press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about stationary waves. Basically, stationary waves are experimental technique used for determination of wave parameters like frequency, wavelength, wave velocity, etc. Right? Now, a stationary wave is formed when two identical progressive waves traveling in opposite directions are superposed on each other. When a stationary wave is formed, it consists of a series of alternate nodes and anti-nodes. Point number one. Point number two, the region of space between two successive nodes is called as a loop or a segment. When a stationary wave is set up in a medium is divided into large number of segments or loops. Now, fourth point, right, the distance between two successive nodes and two successive antinodes is lambda by 2, where lambda is wavelength of stationary wave, which is same as the wavelength of two component waves, right? Those form stationary wave. The distance between a node and an immediate antinode is lambda by 4. These two concepts we are going to use in our next discussion. Now, nodes are the particles of medium which are always at rest due to a stationary wave set up in the medium, right? Now, particle velocity or velocity of simple harmonic motion or velocity with which particles vibrate is 0 at nodes, and also amplitude of vibration is 0, but the pressure is maximum. So, at nodes velocity is 0, mean velocity of simple harmonic motion is 0, amplitude is 0 and pressure is maximum. At antinodes, velocity of vibration, that is velocity of simple harmonic motion, is maximum, amplitude of vibration is maximum and pressure is minimum. And all particles in a given loop vibrate with same phase. That means in that loop all the particle, right, suppose at any instant of time, right, one particle is in mean position, then all the particles in the loop are in the mean position. But the moment all the particles reach their maximum displacement position, right, in upward direction or in downward direction, that means there is no phase difference between any two particles in a given loop. However, when we consider the adjacent loops, right, the particles in the adjacent loops are out of phase or having a phase difference of pi or 180 degree, because if at any given instant of time, if a particle in one loop is moving in upward direction or in positive direction, then the particles in the neighboring loop start moving in downward direction, that is negative direction. So now we are going to discuss two types of instruments, musical instruments in fact. Stringed instrument and air instruments. Now veena, guitar, violin, sitar, etc. are stringed instruments, right? They consist of several number of string, right, rigidly fixed between 2 points on a sound board, right? Now the sound board, shape of sound board is different for different instruments, right? Now next, shahanai, flute, trumpet, etc. are air instrument, right? So we are having a stringed musical instrument and air musical instrument. Now we will take vibrations in a stretched string. Vibrations in a stretched string. So a thin metallic wire, right, stretched between two rigid supports is called as a stretched string. Right here, a thin metallic wire stretched between two rigid supports is called a stretched string. Suppose you might have seen the instruments like veena, guitar, sitar, etc., where several thin wires, right, are stretched between 2 points. So one is rigidly fixed, and the other end is right, is connected to a screw type structure, right, where we can vary the stretching force applied on it. Just you might have seen that whenever we are stretching a rope or a nylon wire, right, for drying the wet cloths, right. So what we do simply is we will tie one end of that nylon rope to a nail or a hook, and we will stretch as much as possible, right, and that the stretched wire whose the other end is again tied to another nail or hook, right. So before tying at the two ends, the string is stretched by applying external force, right. When a string is stretched by applying the force, an internal force is developed in the string according to Newton's third law of motion, right. We know that for every action there is an equal and opposite reaction, right. That internal force, right, developed in the string, right, which is also called restoring force, right, after the wire is stretched is called tension in the string, right. So here this is say this is wire, the end a thin wire is stretched between these 2 points, right. Now let us consider a wire of length L and linear density or mass per unit length M, right, stretched between 2 points A and B. Let T be the tension in the string. So generally we will tie one end of the string to end A, then we will stretch it, and we will fix the stretched end, right, to the point B, and this arrangement is called as a stretched string. So when we pluck the string, at any position, even in the middle or at the position A transverse wave is generated in the string. Say like that. Now this is the previous position of the string before plucking, and now a transverse wave is generated in the string like that, and it travels from A to B with a velocity v, right. Now this velocity v, right, is the velocity of the transverse wave traveling along the length of the string. Now at the end B, it meets an obstacle and it gets reflected, just like when right, a torchlight is focused on a mirror, the light get reflected from the mirror, here it gets reflected. If the crest is incident on it, it reflects as a trough. Right. Generally, the size will be same. Right here, some have written it like that. Right. Now, the reflected wave traveling with the same velocity v from B to A, right? It superposes on the direct wave, right, forming a stationary wave, right. Now the string is vibrating with a number of loops, right. Now these vibrations are called transverse vibration of a stretched string. So the sounds produced by stringed instrument like veena, guitar, etc. are due to transverse vibration of this stretched string, right. So in the stretched string, a transverse stationary wave is formed, right. But due to the vibration in the string stationary wave is formed, but in air, right, longitudinal sound waves are produced, right. We can able to hear that sound, right. Now this is the velocity. Now the velocity of right, velocity of wave on string is given by v is equal to square root of T by m, where T is the tension in the string, right. Now where T is tension in the string and m is equal to m by L is called mass per unit length of string or linear density. Volume density of a body is mass by volume, and linear density of a string or a wire or a rope, right, is the mass per unit length, where m is mass of string and L is length of string. Remember this equation. We know that velocity of a mechanical wave in a material medium is given by V is equal to square root of elastic property and right, inertial property. Here elastic property is represented by Young's modulus and it is equal to tension in the string, and inertial property is represented by linear density. But in the case of gas, we have taken bulk modulus, which is equal to gamma times the pressure, right, and we have taken density of the gas. Remember, V is equal to square root of gamma into P by rho. Right? Here, since this is a wire, when a wire is stretched, right, now the stress is longitudinal stress, the strain is longitudinal strain, and the elastic constant, the ratio of stress to strain, is called as Young's modulus, right? So T is tension in the string. Remember that small m is mass per unit length, which is equal to mass of the string m divided by length of the string L. Is it clear? Now, when it began to vibrate, now the frequency of vibration, it depends on number one, tension in the string T, number two, length of string L, number three, mass per unit length, small m, and the most important thing is it is a modes of vibration, right, of the string. It depends upon modes of vibration in the string. You might have seen a guitarist playing guitar, or somebody is playing that veena, right? So when you see that there are some screw-like arrangement at one end, and at the other end of the string they are fixed, rigidly fixed. Sometimes you might have seen they are adjusting the screws. That means they are changing the tension. And when the string is plucked by the right hand, you see the motion of the left hand. The left hand will press the string at different positions, right? When the string is pressed, say at this point, then only this length of the wire began to vibrate. When it is pressed here, only this length of the wire began to vibrate. Therefore, they can change the length of the wire with the help of the left hand. With the help of the screw at one end of the string, they can vary the tension, and using the left hand, they can vary the length. Using the right hand, they can pluck the string. And generally, there are 4 or more strings. Carefully observe that one, right? They are having different thickness, right? That means if a thick wire means more mass per unit length is more, right? If it is a thin wire, then less mass per unit length is less. So by changing the string, right, or wire in the instrument, they can vary mass per unit length, and by changing using the left hand, they can vary length, and using the screw, they can vary tension, and they can produce different frequencies in the same instrument. And now what is mode of vibration, right? So now I will explain what exactly is mode of vibration, right, in stretched string, right? Now it is applicable, right, to string only, my explanation, right? In ear explanation, right, when we go to the ear instrument or ear column, right, we will have slightly, right, difference in that, right? Now the modes of vibration in the string, that depends upon number of loops formed. It depends upon the number of loops formed, right? It may vibrate with one loop, It may vibrate with 2 loop or 3 loop or 4 loop or n number of loops, right? So when the number of loops changes, we say there is a change in mode of vibration, right? Is that clear? Right. Now remember here, a stretched string with tension T, length L and mass per unit length, a transverse wave on a stretched string travels with a velocity v is equal to square root of t by m, where t is tension in the string, m is linear density or mass per unit length. The frequency of vibration of a stretched string depends upon 4 factors: tension, length, mass per unit length and modes of vibration, right? Now when a string, we say take, this is the string, it is A, B, length L with the tension T. When it is vibrating with one loop, so here we have, here this is a node, this is a node. So two nodes are always formed at the two fixed ends of the wire, because since the end is rigidly fixed, right, the particles at the end of the string will not vibrate, they are rigidly fixed. Therefore, in case of a stretched string, two nodes are always formed at the two fixed ends, and we know that in a stationary wave, nodes and antinodes occur alternately. There is a node between two antinodes and there is an antinode between the node, and this is the antinode. Here the particle is vibrating with the maximum amplitude. So here this is vibrating with one loop with one antinode and two nodes. It vibrates with one antinode and two node. Now this mode of vibration is called first mode of vibration, and it is also called the fundamental mode of vibration. It's called fundamental mode of vibration, and the corresponding frequency is called as a fundamental frequency. Remember, in the chapter sound, while discussing the characteristics of music, that is pitch, loudness and quality, that quality of musical sound depends upon that number of harmonics I said there, right? And now continuing at this point, right, the term what I have used, right, while explaining that quality, that is the number of harmonics present, right? Now I am explaining that one. It is called fundamental frequency, right? If any vibrating body vibrates with the lowest possible frequency, then its frequency is fundamental frequency. In fundamental frequency of stationary wave, right, minimum number of possible nodes and antinodes are formed. So here the minimum number of nodes is 2, because at the two ends there is always two nodes, and one antinode is always formed between two nodes. Therefore, here the string is vibrating with one loop with the minimum possible number of nodes and antinodes. Right. Now, suppose if the string is now if the string is vibrating with two loops, now this is two loops. Now see here, node, here is a node, here is a node, and antinodes between two successive nodes. So here let us count the number of nodes and antinodes. Here we have two antinodes and three nodes. Here two antinodes and three nodes are formed. Right. Now there is an increase in the number of nodes, right, and number of antinodes. Now we see this length is lambda by 2. The distance between two successive nodes. Now, this length is equal to lambda by 2. That means wavelength has changed. Consequently, when wavelength changes, here velocity remains the same because it depends upon the tension in the string and mass per unit length. It is nothing to do with the number of nodes and antinodes. But when number of nodes and antinodes change, or number of loops change, wavelength change, consequently frequency changes, and this is called second mode of vibration or first overtone. It is called first overtone, right? This frequency is called first overtone. Right, this is called second mode of vibration, and the frequency is called, right, first overtone. Suppose so now here it is vibrating with three loops, that means 4 nodes and 3 antinodes. Right. Now this mode of vibration, right, we have 3 loops, 3 anti-node and 4 node. Now this is this is called third mode of vibration, and this is called second overtone. Suppose if F1 is the frequency of fundamental frequency, F2 is frequency of first overtone, F3 is the frequency of, right, third overtone, right. Similarly, right here F1 is less than F2, it is less than F3, right. So if again we are having 4 loops, 5 loops, 6 loops, 7 loops, etc. For the same value of tension T, same value of length L, and same value of mass per unit length, but the string can vibrate in different number of loops, right. So these are called modes of vibration. This is fundamental mode of vibration. This is second mode of vibration. Its frequency is called first overtone, right? And this is third mode of vibration, and its frequency is called as second overtone. Now, what is overtone? Right here, see, this F2 is greater than F1. Also, F3 is greater than F1. That means those frequencies F2, F3, and of course F4, F5, F6, etc. When 4, 5, 6, etc. loops are formed, are higher than the fundamental frequency. What is fundamental frequency? The lowest frequency with which the stretched string, or as a matter of fact any vibrating body vibrates, is called as fundamental frequency, right? So, in this case stretched string, the lowest frequency with which a stretched string vibrates is called fundamental frequency. Corresponding mode is called as fundamental mode or first mode, and it has a one loop, one antinode, two nodes, right? And what is an overtone, right? The frequencies of vibration of stretched string which are higher than the fundamental frequency are called overtones, right? The frequencies, right, which are higher than the fundamental frequency of vibrating body are called overtones. There may be first overtone, second overtone, third overtone, etc. Right? I think you can able to understand, right? Now, when remember that whatever it may be, in case of stationary waves, right? If a stationary wave is said to be vibrating with, right, fundamental mode, it vibrates with minimum possible number of nodes and antinodes, right? And in general, what I am telling, not only to stretched string, it holds well for air column. When we go from one mode to next mode, there is an increase in one node and one antinode. You see, now we fundamental mode, one antinode, two node. When we go to the next mode of vibration, now you see there is an increase in one antinode, there is increase in one node. So when we go from first overtone to second overtone, that is the next mode, immediately next mode. Then again, here 2 plus 1, 3 antinodes, 3 plus 1, 4 antinodes. Remember that when a stationary wave changes from one mode to next mode, there is an increase in node by one number, and there is an increase in antinode again by one number. Right? Is that clear? Now, here the lowest frequency with which a body vibrates is called fundamental frequency. Is called fundamental frequency, and the corresponding mode of vibration is called fundamental mode of vibration. Now, the frequencies of vibration which are higher than the fundamental frequency are called overtones, right? So frequency of first overtone is greater than fundamental frequency of second overtone is greater than, right, first overtone, third overtone is greater than second overtone, so on. All are called, except the fundamental frequency, all other higher frequencies at different modes, because in one loop fundamental mode, two loop first overtone, three loops, right, third overtone, right, I mean second overtone, right, it can be n number of overtones, right. And now here again remember, we are using very important term here, the frequencies of overtones which are integral multiples of fundamental frequency are called overtones, I mean harmonics, harmonics. So the frequencies of overtones which are, right, integral multiples of fundamental frequency are called harmonics, right. So fundamental frequency, we have overtones and we have harmonic, right. So here, so harmonic is equal to n into fundamental frequency where n is equal to 1, 2, 3 etc., an integer. It is an integer, right. When we put n is equal to 1, so we get first harmonic is equal to, when n is equal to 1, we get first harmonic. First harmonic is always equal to fundamental frequency. First harmonic is always equal to fundamental frequency. Suppose if I take f1 is equal to 100 hertz, that is the fundamental frequency. Now frequency of overtone is equal to, next overtone is 200, f3 is 300, f4 is 400 hertz etc. Then this is the fundamental frequency and is called first harmonic. So fundamental frequency is always equal to first harmonic. Now you have to see here, this is 2 times the fundamental frequency, n is equal to 2. So this is called second harmonic. This is if the frequency of overtone is 3 times the fundamental frequency, then it is called third harmonic, fourth harmonic etc., right. So remember all these things: fundamental frequency, overtone, harmonic, right. A harmonic is equal to n into fundamental frequency, right. So when n is equal to 1, the first harmonic is equal to fundamental frequency. Next, second harmonic 2 times the fundamental frequency. Third harmonic, right, 3 times the fundamental frequency. Fourth harmonic 4 times the fundamental frequency, right. Now that relation between overtone and harmonics, that depends upon the instrument, right? So depending upon the instrument, right, second harmonic may be equal to first overtone, may be equal to third overtone, right? That we will discuss, right, stretched string and the air column, right? Now this is the most basic things we have discussed, right, in the vibration of a stretched string. Generally, for any vibrating body, right, lowest frequency of vibration is called fundamental frequency. Frequency higher than the fundamental frequency are called overtones, and the frequencies which are integral multiples of fundamental frequency are called harmonics, right? Now, we will take a derivation, right? It is important for board examination, right? Now, modes of vibration in a stretched string. Here, we will discuss the relation between fundamental frequency and right, harmonics, mean overtones, right? Here we will discuss all the things: fundamental frequency, first overtone, overtones, and harmonics of a stretched string. Now, let us consider a string of length L stretched between the 2 points E and B of tension in the string T, mass per unit length N. When a string is plucked at one end, a transverse wave propagates with a velocity V from end A to end B along the length of the string and reflected from the point B. The reflected wave is identical to the incident wave in all respect except the fact that it is travelling in opposite direction. The reflected wave superposes on incident wave, forming a transverse stationary waves, right? So, in fundamental mode of vibration, the string vibrates with the minimum number of possible loops and nodes, loops. Minimum possible number of nodes and antinodes. And since the two ends A and B are fixed, two nodes are always formed, right, at the two ends. So this is a node, this is node, and an antinode is formed between them. Between them, an antinode is formed. Here, now this is called, right, first or fundamental mode. This is first or fundamental mode, right? If F1 is fundamental frequency and lambda 1 is fundamental wavelength, then we have that formula relation between velocity, wavelength and frequency. So V is equal to lambda 1 into F1, or F1 is equal to V by lambda 1, right. So if lambda 1 is the wavelength of the wave in fundamental mode, then what is the distance between the two successive nodes or length of a loop? L is equal to lambda 1 by 2, right. So or F1 is equal to substituting lambda 1. So this lambda 1 is equal to 2L here. So that this is 2, that is V by 2L. Let us take it as equation 1, and is called fundamental frequency, right. So here F1 is the fundamental frequency, V is a velocity of a transverse wave on the string, and L is length of the string. Now we know that in the next mode of vibration, the string vibrates with two loops. Here one loop, one antinode and two nodes. Now here this node, this is antinode, this is antinode. Here we have, right, how many loops? Two loops, two antinode and three nodes are formed here, right. Now here, now in this case, right, this is the second mode of vibration. In this mode of vibration, wavelength changes, correspondingly frequency changes, and that frequency is called frequency of first overtone, right. Now if F2 is frequency and lambda 2 is wavelength of first overtone, then so frequency of first overtone, directly I will take, we have written here, then the frequency of first overtone F1 is equal to, F2 is equal to, again this is V by lambda 2. Again remember I have told that velocity depends upon T and M. There is no change in T, M and L here. Only the loops are changing, or number of nodes and antinodes are changing, right. But here when I take this length L, here this is lambda 2 by 2 and this is lambda 2 by 2, this length, and therefore length L is equal to, right, lambda 2 by 2 plus lambda 2 by 2 is equal to lambda 2, right. Therefore F2 is equal to V by, right, lambda 2, or this is equal to 2V main, this is lambda 2 is equal to L, or it can be written as 2V by 2L multiplied by 2 divided by 2, or from this one F2 is equal to, right, taking 2, Now we left with V by 2L. Right? Let us take it as equation 2. So that means here F2 is equal to 2 times F1. So this F2 is first overtone but second harmonic, right? The first overtone frequency is 2 times the fundamental frequency. Now here, when I take it, the next mode of vibration, here it vibrates with 3 loops, A, B, right. So node, 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 anti-node, anti-node, anti-node. So here we have, in this case, 3 loops, 3 antinodes and 4 nodes, right? So from one mode of vibration to the next mode of vibration, there is an increase in one node and one antinode, right? So this is called, right, third mode of vibration. This is the third mode of vibration. Suppose if F3 and lambda 3 are of second overtone, right? That means F3 is frequency of second overtone, lambda 3 is wavelength of second overtone, then F3 is equal to V by lambda 3. So here this length is lambda 3 by 2, this length is lambda 3 by 2, this length is lambda 3 by 2, right? So here L is equal to 3 lambda 3 by 2. In this case L is equal to 3 lambda 3 by 2, right? I will write it here. Right. So here L is equal to 3 lambda 2 by 2, mean 3 by 2. Then lambda 3 is equal to 2L by 3. That implies F3 is equal to right. So 3V by 2L or F3 is equal to 3 into V by 2L. This is equation 3, that is F3 is equal to 3F1. So the frequency of second overtone is 3 times the fundamental frequency. That means here second overtone is equal to third harmonic. Similarly, we can show that here F1 is to F2 is to F3, etc. is equal to 1 is to 2 is to 3 is to, etc. That means the frequencies of overtones of a stretched string are harmonics of the fundamental frequency, right? So here both odd harmonics like F1, 3F1, 5F1, 7F1 exist, and even harmonics 2F1, 4F1, 6F1, etc. exist, right? Now there will be a 5-mark question on this particular topic, right? That is, they may ask, show that the frequencies of overtones of a stretched string are, right, harmonics of the fundamental frequency. Is that clear? Now let us conclude at this stage. So we have shown that what we have shown, F1 is to F2 is to F3 is equal to 1 is to 2 is to 3, etc. That means frequency of overtones of a stretched string or harmonics of the fundamental frequency, or right. Now the stretched string consists of all possible harmonics, first harmonic, second harmonic, third harmonic, fourth harmonic up to nth harmonic, right. Okay, right. Let us stop at this stage and we will continue it in the next class. Thank you very much.